So when we're looking at equilibrium, one of the things we have to consider is something called Le Chatelier's principle. Now, Henri Le Chatelier and a German scientist, Braun, independently both observed and formulated this concept, this principle that recognizes that when you have a system in equilibrium, anytime you stress the system, when you alter some of the conditions, what ends up happening is the reaction itself will shift, either make more product or make more reactant, to get back to that equilibrium point, that equilibrium constant, that proportionality of product to reactant. So when the conditions change in a system, what am I talking about? Concentration of reactant or product. If it's a gas, it's sensitive to pressure and or volume, because those two things are interconnected and move in opposite directions with gases. If I change the temperature, especially if it's a reaction that is strongly exothermic or endothermic, but even if it's not very strongly either way, if it has any sort of thermal component in terms of being exothermic or endothermic, it's going to be sensitive to temperature as well. And so we're going to look at each of those situations. So when the conditions change, the system shifts to restore or to find a new balance point so that it gets back to that proportionality of product to reactant. Okay? Let's look at an example. The decomposition of hydrogen iodide. Okay? So hydrogen iodide gas will break down into hydrogen gas and iodine. At equilibrium, at 800 K, the constant is 0.016. So if I have 0.69 molar concentration of hydrogen iodine gas in the chamber and 0.11 molar of hydrogen and of iodine, that system is at equilibrium. If you do the proportionality, it comes out to be approximately 0.016. What if I add more hydrogen iodide? If I add more HI, it's going to shift to the right, because now all of a sudden the denominator of the equilibrium relationship will become larger. And so the value we would calculate for K, or the Q at this point, would be smaller than 0.016. And so this system, this reaction, will shift to make more product and take away some of the reactant to get back to that 0.016 ratio of products to reactants. If I were, on the other hand, to add some more hydrogen gas or some more iodine gas, that would push the reaction back in the other direction and shift it to the left. Because now there'd be more product than reactant proportionately, and so the value would not be 0.016, but some value larger than that, and so we'd have to shift to get back to 0.016. A little bit less product on the top, a little more reactant on the bottom. Okay. So, and the same could be true if we were to take away some of the product. If you had a way to remove one of the products, you could continue to drive the reaction forward. And in industry, whenever we're producing chemicals, whenever we're producing materials that come out of an equilibrium state type reaction, part of the strategy to maximize the amount of product is to find a way to isolate or sequester or harvest the product as it's getting made, so as to convert as much of the reactant into product and keep the reaction moving forward. Now, I said if it's a gas, it's sensitive to volume and pressure, because those two things are intertwined. Decrease the volume, you increase the pressure. Increase the volume, you decrease the pressure. So if I increase the pressure or decrease the volume, like if it's a piston system where I have a set volume but I can squeeze it into a smaller space, what happens is that the reaction is favored to where there is less moles, whether that's on the reactant side or the product side. You have to look to see, well, are there the same amount of gaseous moles on both the reactant and product side, or does one side have more and one side have less? Whenever one side has more and one side has less, the reaction is going to shift in the direction when I increase the pressure or decrease the volume. It's going to shift to where there are less moles, where there are fewer moles. And conversely, if I increase the volume, decrease the pressure, then there's, in effect, space for more moles of gas. So the reaction will be favored in the direction where there are more moles. If they're the same amount of moles on both sides, guess what? Pressure and volume don't change it. There's nothing to shift it. Also, and sometimes in AP land they like to throw this in here, if I introduce an inert gas, something that's not going to react with the reactants or the products, even though in effect the overall pressure has changed, since it's not involved in the reaction, it doesn't change the direction or the balance point. The system does not have to shift to fix the equilibrium because the pressure impact is equal on both sides. And what you introduce is not a player in the reaction. Temperature. Remember I said when we looked at thermodynamic equations that we can write the actual delta H value, the heat, as a reactant or a product. If it's an endothermic reaction, then heat energy is going into the system. It's as if it were a reactant. And if it's exothermic, then heat's coming out as if it were a product. It is a product. So, if I change the temperature conditions, that actually changes where the K value lies because, although I'm not adding or changing the concentration of reactant or product, I am, in effect, altering one aspect that's not material but is energy. So, if it's exothermic, to add heat is to drive it left because it's like adding a product. To lower the temperature is to take heat out. That's removing or reducing a product so it drives it to the right. If it's endothermic, where the delta H is a reactant, the opposite is true. So therefore, if I'm adding heat energy, it's like I'm adding reactant, I'm driving it to the right, I'm moving it forward, if you will. And if I'm lowering the temperature, I'm taking reactant away. So I'm driving it from product back to reactant. I'm making it shift left. Reaction here. Nitrogen gas and hydrogen gas to make ammonia. So over on the reactant side, I have a total of 4 moles of gaseous material. On the product side, only 2 moles. If I compress the container that this reaction is happening in, when it's at equilibrium, when it's reached that dynamic balance, what ends up happening is that I shift it towards making less moles. I drive it to the right. If I increase the volume or decrease the pressure, then more moles are favored, and so this reaction would shift left. There's no hard and fast, oh, it always goes right, it always goes left. You have to look and see what's the relationship of the total number of gaseous moles of gas, not aqueous, not solids, not liquids, of course, because those don't factor into the equilibrium calculation at all anyways. Right? If I were to look at the heat of this reaction, this is an exothermic reaction. So if I lower the temperature, then I'm taking heat out, I'm driving it forward to make more ammonia. If I raise the temperature, I'm adding product and driving it back to the left. So, the Chatelier's principle basically says a system in equilibrium, if I change something, concentration, volume or pressure if it's a gas, temperature, it's going to shift to get back to equilibrium. So the amounts that were at equilibrium may become different because I've changed something, but always to try and get back. It's sort of the rubber band principle. You can stretch it, but it always wants to go back to where it was, its original shape. Okay? Same thing here. Reversible reactions at equilibrium want to stay at equilibrium. And if you do something to alter one aspect of it that impacts the equilibrium, add more reactant or more product, or take something away, change the space it's happening in or the amount of pressure, as long as it's something involved in the reaction, or change the temperature it's happening at, all of those things can shift where the equilibrium lies to get back to what the equilibrium constant is.